Synchronous here means so we're using um, first in, first out, but we are starting off from the last message, assuming that this took the first preference or priority in terms of the message being transmitted. So in this scenario, we're assuming that this message came in first. So we have to start looking at it bit as the first in, right? First in, first no, I think it's first in, last out, more or less. Okay, so if you look at it, for instance, the reordering of the message will end up with this coming through first, followed by this, followed by that, followed by that. Look at the order here. To address the message order at the receiving end, starting from this message, followed by this, that, and that. The multiplexing arrangement has to go the reverse format. That's where we're having the last in becomes the first to take preference. So we can be able to sort it out when it gets to the receiving end. So we do have, so if you look at it carefully, if you look at this set, for instance, you'll notice that the one which is coming from here will be the first to be delivered at the receiving end, which would coincide with the way it was originally set as the first message. And then the second one, watch again. So the second one, which was a 1. So the second is a 1. So if you 1, 1, 1, 1, 1. So in terms of rearrangement, you'll come back to the same format. So we'll get this at the other end. But when it comes to multiplexing synchronously, we went the reverse way, so we can able to address the correct order in which the message came in. Okay, so like I said, so in a way, if you look at it from first in, first out, it wouldn't really work over here. In this, it wouldn't work with the multiplexing and the synchronous and division multiplexing. Ideally, the best way to achieve the first in, first out is by going with uh, uh, the last in, first out. No, the last in becomes the last out, basically, yes. So the last in, so the last 0 becomes the last from this side, and then the, the oh my goodness, this is crazy. Reorder the bits in multiplexing. Okay, let's go all over again in terms of the frame rearrangement. Okay, I'm trying to use first in, first out, and it's not really working out very well. I think the correct order should be uh, uh, first in becomes the last out. Yes, in that sense, you would get your arrangement perfectly. So the first in will become the last out, and the last in becomes the first in or the first out. So right, you see? So the first in became the last, and the last in became the first. So the same approach. First in, and the last in became the first out. So first in became the last, and the last in became the what? First out. Yes, so in that sense, it would just reorder it at the receiving end properly the way it's supposed to go or flow. It's quite interesting, very when it comes to dealing with the arrangements of bit sequence, when it comes to switching within multiplexing, it's a bit trickier, a bit tricky, you know. But all of this happens in in a flash, you know, a speed of light. It's able to organize it properly based on the algorithm or implementation that's been put in place at the multiplexing level. And it's able to rearrange the bits, the message, so they can be delivered in the right order at the receiving end. So that's how the arrangement goes, I guess. And it looks like there are some disadvantages, right, when it comes to synchronization, time division, multiplexing. The message can fall off in order, especially when the when one of the bits is dropped or gets corrupted or gets lost in transmission. Then the order start becoming a bit of a challenge. So you notice this was missing its bit. This was missing completely its bit. And you notice how it affected the arrangement. Yeah, it really affected the sequence. Now let's move on. Another statistical multiplex. Another multiplexing is a statistical multiplexing, which deals on time demand basis as it relates to time division. So schedules link in a pair packet by basis. Packets from different sources are interleaved interleaved on links, and buffer packets are switched so that it can address contention within a link. See any problem when it comes to this arrangement of statistical multiplexing? Any arrangements or any problems? Maybe. So in that, if you looking at the problems from the statistical multiplexing point of view, implementations or strategic implementation such as FIFO, LIFO, or quality of service becomes the fair allocation of how the link's capacity is maximized. In other words, there has to be a strategy in place when it comes to statistical multiplexing. The application needs to break up its message into packets and reassembles it at the receiving end. So fair allocation of link capacity is important, where strategies like LIFO or quality of service, sometimes even FIFO, can be adapted. Buffers may overflow, and that could lead to congestion at the switch levels. So an example of that. So synchronous time division and statistical time division. And you can tell some of the difference between the two in terms of lines now having messages, but still have a particular link that also needs to be multiplexed, and then it creates gaps. On the other hand, with statistical, it all just uh, puts the most respective uh, informations together and just forwards them as and when, or based on their their, their time of um, of entry. So FIFO, first in, first out. So if in this case, if A1 was first in, then obviously would take up the upper hand in terms of its carrying the message forehand at the front level. And then B1 would take over, um, followed by D1. And then if there's nothing on this link, on link or line E, nothing is captured, and it just goes right up to the second frames of packets or second lines of packets to pick up as the first in, first out. Interesting stuff, man. I'm even getting confused myself. But anyways, these are just conceptual look views of how uh, time division multiplexing handles the various bits that comes in into a switch for multiplexing and what have you. Okay, so don't draw so much on it. Okay, so now moving on, we've covered the switch network at the circuit switching part. Now let's move on to the packet switching part, where data is sent in discrete portions, with the internet being a key uh, reference. So in packet switching, we have each end-to-end data streams are divided to packets. A user A, B packets are shared or shared the network resources, and each packet uses full link bandwidth. Resources, on the other hand, uh, its usage-wise as very important and needed. But since we haven't a way of since the packets are being since the information or the data streams are being divided um, into packets, aggregation of resources is it's much more better as compared to the sequestration or resource of frequencies and what have you, and allocations are much better or much more efficiently managed within packet switching. So resource contentions aggregate resources demand can exceed the amount available. Congestion packet queues wait for links to use, stores and forward packets moves one hop at a time, and nodes receive complete packets before forwarding them. So this is some of the resource contention that you'd find within packet switching, but generally it's an end-to-end data transmission, which involves those data to be split up into packets, and mediums are shared to address network resource needs, and each packet uses full length bandwidth allocated to it. So here we look at some of the messages transmission within packet switching. And there's the question is, why not message switching? Well, if it's applied circuit switching over here, the transmission will be a whole lot different in terms of how propagation delays are addressed. So in this scenario, we just look at how the message is forwarded from based on the negotiation between the various end devices. Information is or messages is transmitted through the two medium or the two network nodes with split up packets, and time is not of essence over here. So until all the messages that have been split up gets to the second node, it's when they get reassembled before they can actually be handed back to the and device that's requesting, or the destination device that's requesting the message. So that's where store and forward comes into play. Calculation wise, if we did have a message from one host to another, and for simplicity purposes, we want to ignore processing and propagation delays. You do have a message that carries a 7.5 megabits of capacity, and it's been transmitted over a medium that can only support 1.5 meg per second transmission. So if you want to calculate transmission delay, that's obviously going to be how many mediums are you dealing with. You can have three of them. You can have three uh, transmission mediums involved that you need to make provision for its delays. So there's going to be the transmission delay from host 1 to node 1, transmission delay from node 1 to node 2, and transmission delay from node 2 to host 2. And in general, transmission delay is calculated as the message divided by the transmission bandwidth times the number of transmission delays involved. So in this case, with 3 times 7.5 divided by 1.5, and that will give you 15 seconds. So that will be the transmission delay involved. Yeah, because you have 3, so you do have to deal with this delay, that delay, that delay, and then multiply by the message itself and the rate that it has, or the band that it has to address transmission. So this is the calculation. So you do have your 1.5, 1.5, 1.5. So that's 3 times the message itself, the data itself, and then the rate of the transmission between the various nodes or host devices. So another elaborate way of looking at packet switching. More on that. Same concept. Okay, so let's look at the variation between packet switching and circuit switching. Packet switching allows more users to use the network, whereas circuit switching does not support that because of how it allocates a dedicated path and dedicated frequency for given transmission, especially if it's using the frequency division multiplexing for calls. So each user here uses a given amount of bandwidth when active. And so 10% of the time is just what has been used per given user. But on the other hand, with a circuit switching 10 users, your packet switching 35 is the probability that there are 11 or more simultaneous active users will result in an approximation of 0.00004 seconds being used for the transmission. In other words, packet switching is a winner. Great for busty data, resource sharing, simpler, low cost setup, excessive congestion though, packet delays and losses, protocols needed for reliable data transfer, as well as congestion controls. But question-wise, how to provide circuit-like behaviors when it comes to packet switching? Then you want to deal with the bandwidth guarantees needed for the audio and video apps. But still an unsolved problem though if you want to look at how circular messages are being transmitted over a packet switching network. Like for instance, you want to transmit a voice transmission over a packet switching network. You can have a lot of challenges. Okay. But like I said, over the years, some of these things have been resolved properly. Now you can make voice calls over what you call voice services, voice over IP, which is voice over packet switching networks. Okay, so now some of these have been resolved in the sense, in a way, to make circuit-like behaviors to be addressed or messages to be addressed within a packet switching network. Advantages wise, packet switching does have statistical multiplexing and therefore efficient bandwidth usage, and it's simple to implement. When it comes to disadvantages, packets switching over circuit switching, we do have excessive congestion, packet delays, and high losses. Protocols needs for reliable data transfers and congestion controls are also some of the disadvantages that you have to deal with, especially when you have systems that have not been well implemented to really handle some of these uh, issues within packet switching networks. Packet head overheads adds or packet headers adds a lot more overheads to the message being transmitted, and they also provide no transparency to a user, especially from the analog point of view. And we're using a road versus a railway. Packet queues and router buffers. How do loss and delay occurs? Usually occurs when you do have packet queues on a router buffer. So when the routing table is saturated with a lot of packets being queued up, then you can have a lot of issues with delays. So packet arrival rates to link exceeds output link capacity, and that causes packet queues and wait for your turn. So you have delays being observed and creating maybe transmission time challenges. So that's an illustration diagram to show you that the lake has been stacked up waiting for deliveries. Four sources of packets delays are the nodal processing and queuing. The nodal processing, we're looking at how to check for bit errors, determine quick determine output links. And for queuing, look at time waiting at output links for transmission, and it also depends on congestion level within the particular router. So the more you have, then the time delay for the nodal processing becomes higher. And you do have some calculations over here that relates to how nodal delays are computed and queuing as well, which you can go through later. Packet losses, queue preceding links in buffers has finite capacity, and when packets arrive to full queues, packet is dropped. Lost packets may be retransmitted though by previous nodes. For source end systems, or not retransmit at all. So it all depends on the system itself. Okay, so with that said, we can probably end our packet switching, and or we'll probably end our uh, communication network, where we talk more, where we covered uh, uh, switch network and broadcast networks. Okay, and then the switch network, we looked at packet switching and packet switching. All right, and there are quite a number of calculations involved, and a number of concepts that needs to be understood clearly. Now to address our multiplexing of some of these messages, either based on frequency or time division, can be used to address communication needs within various implementation. And then when it comes to packet switching, then you're looking at how uh, queuing issues can be addressed since we're dealing with store and fork. So obviously, bandwidth and uh, transmission delays and other congestion delays or errors could factor into the packet switching. One of the key issues, some of the issues that needs to be looked at. So with that said, we've covered chapter 10 from 10.1 to 5. Will be the required reading in the textbook. So if you want to really get an in-depth understanding of what's the switching concept or theory is all about, this chapter deals a lot with that. Okay, so that should do it for the for this lecture, or yeah, for this lecture, which is lecture 4.